So, hello everyone, my name is Julien Duboc. I work in Lausanne in Switzerland with Eric, who presented the study of the tunnel yesterday. And today I'm going to present you another structural analysis in which we carried out a performance-based design approach. So let's start with a few words about the project. So this is a new complex of the Swiss audiovisual company. You can see our pictures here. We have 4 distinct buildings which are connected to each other with a hall in the first floor and with an open space in the second floor. We have different uses for this complex. So radio studio for the production, broadcast, also offices, administration activities. So it's a structural analysis. So we focus on the fire resistance of the structure. So for this building, and according to the Swiss regulation, we have a requirement of 60 minutes. So for the buildings, there is no specific issue as they were designed according to the Eurocode 2 with a good covering for the rebars. But it's not the same for the hall and the open space because we find steel members, so with ceiling beams and truss members. We can see pictures here in the bottom. So we cannot achieve the R60 requirement for the steel members, both for the hall and for the open space. So we had to find solutions to improve the situation. So it can be passive protection such as fire panels or intermittent coats, but due to the height of the buildings and also the connections between beams and truss members, these options seem to be very expensive. So we had to find another solution, and it was a performance-based approach based on the risk analysis for these specific areas. So the goal of the PBD approach is, of course, to reduce or optimize the need of passive protection, so based on a natural fire approach. So if we focus on the risk for the areas, we have a hall with exhibition, reception, and open space with offices. So we have a fire load density, so which is quite moderate. We have a full sprinkler project as well, with probably a good reliability. And also, we see it on the pictures, we have large windows on every facade, so very good conditions of ventilation, which is quite important. So we can qualify the risk as moderate for these buildings, which gave us real chance to make some savings with this kind of approach. So let's focus on the scenarios and on the real risk for this building. So according to the Swiss regulation, the hall and the open space are considered as inner courtyard, in which we have a maximum fire load density allowed, which is 500 megajoules per square meters. So this is a first scenario. We can have uniformly distributed, uniformly fire load density distributed over the entire area, up to 500 megajoules per square meters. But more specifically for the hall, so we have receptions, maybe some events during the year, exhibitions, so it could be probably more localized fire load density. For the open space, it's quite the same. We have offices, maybe rest areas with, I don't know, seats, sofa, or others. So we can have both scenarios, maybe compartment fire scenarios and more localized fire scenarios. So we defined some localized scenario for the whole according to the German standard, which is often used in Switzerland for the localized fire scenario approach. For the whole, we considered this scenario with a maximum heat release rate of 6 megawatts, which is quite representative of exhibitions room. With quite moderate fire load density and more than 100 people, so which is quite representative for our area. And we made a parametric study on the fire area in order to consider different heat release rate per unit area, so 250, 500, and 1,000 kilowatt per square meters. Here we have the scenario, the heat release rate curve for the 3 localized fire scenario we considered. And of course, we considered the compartment fire scenario as well, as we saw before, with an office use, according to the Eurocode 1, Annex E, with a maximum fire load density of 511 megajoule per square meters, which is quite representative with the maximum fire load density allowed for the zone, according to the Swiss regulation. Now for the open space, it's basically quite the same, even if the localized fire scenario is a bit different because it's not the same occupancy, not the same use. So we considered a maximum heat release rate of 3 megawatts, which is representative for an office use with moderate fire load density and more than 100 people. We also made parametric study on the fire area to get the same heat release rate per unit area as we saw just before. Here we have the curves, and also we considered the compartment fire scenario for an office use, still according to the Eurocode 1. So a few words about the ventilation and the firefighting measures we have for the study. So as we said before, we have large windows on every facade with double glazing. So we can consider the breakage windows conditions for this double glazing with 10% of the windows open at the ambient temperature. Then we can consider 50% of the windows open when the temperature reaches 200 degrees and around 90% when the temperature reaches 400 degrees. Also, we have a full fire detection and sprinkler in both the hall and the open space, so we can adapt the coefficient of the fire load density still according to the Eurocode 1. And this consideration is accepted in Switzerland, but only for the compartment fire scenario, not for the localized fire scenario. So we can reduce the fire load density just for the compartment fire. So in first approach, we used a zone model or 2-zone model for the hall and for the compartment for both type of scenario. So here we have the results for the hall with the compartment fire scenario. The blue curve is the gas temperature results with sprinkler installation, so with the minoration of the fire load density. And the orange curve is the gas temperature results without sprinkler. So what is interesting to see is the maximum gas temperature in the upper zone, which is less than 400 degrees. So for the structure, it's very, very good as we have no decrease of the steel resistance. So the steel keep the same resistance as in cold situation. So we can say that the requirement R60 is achieved for the beam, the ceiling beams in the hall. Now for the localized fire scenario, here we have the results for the 3 different scenarios we considered with the 3 heat release rate per unit area. And the conclusions are the same as we have a gas temperature less than 400 degrees. So of course the steel temperatures remain less than 400 degrees. Here we have the result for the open space. So it's a bit different. First thing is the surface of the area, which is used more than 5,000 square meters. So we have still 2 different curves, 2 continuous curves, the blue one with sprinkler, the orange one without sprinkler. And the discontinuous curves correspond to the steel temperature because we made some thermal calculations in order to have an idea of the steel temperature if they were exposed to this kind of thermal stresses. So what is interesting to see on these pictures is that for the sailing beams, the steel temperatures remains under the critical temperatures, so that's quite okay. But it's not the same for the truss members, because we have steel temperatures higher than the critical temperature. So what we can say for this scenario with this zone model approach is that the steel members for the sailing beams are okay, but it's not for the truss members. So yes, here we have the same for the localized fire scenario, just for the heat release rate per unit area of 1,000 kilowatt per square meters. So we can see that for the sailing beams, which is the lowest curve, the green one, we have temperature under 400 degrees. So we can have the same conclusion as for the whole, but it's not the same for the truss members. As okay, it depends of the height, but we can get temperatures higher than the critical temperature for steel. So the truss members are KO. So preliminary results, we consider the first approach with a very simplified model, a two-zone model. We considered compartment fires with and without sprinkler, and localized fire scenario without sprinkler. We saw that the steel members for the whole are okay. We achieved the R60 conditions, but for the open space, it's a bit different. It's still okay for the steel members, but not for the truss members. So it seems that we had a chance to reduce the need of passive protections for these buildings. But now we can ask some questions about limitations of the models. We saw yesterday in the presentation of Niels the limits of the two-zone models in terms of surface area. Here for the open space, we have more than 5,000 square meters, which is used. So we can have some doubts about the results obtained with the zone model, so that's the first point. And then about the geometry of the compartment, we know that for the zone models, they made some assumptions, and of course they considered a very simple geometry, rectangular geometry, as we see here, which is totally different as for our open space, which has a shape over here. So it's completely different with a rectangular compartment. So we carried out the study with a more advanced fire scenario using CFD and FDS in order to consider this complex geometry to see if we can validate or not the results obtained with the zone model. So we imported the complex geometry thanks to the IFC file into PyroSim in order to consider the real complex geometry for the open space. We also defined the same windows breakage conditions for our model with different devices located on the windows in order to consider the different breakage in function of the temperature. We considered a reaction of combustions with, which is representative of an office use with 50% of plastic and 50% of paper. And we consider same fire parameters in order to compare the results obtained with the zone model and the results of FDS. So the same heat release rate per unit area, the same heat of combustions, and the same fire load density. And we considered a uniform mesh size of 25 centimeters for this model. And here we have a picture during the simulation with the windows breakage. So what about the results? So here we have the same graph as before. We just added the results obtained with FDS. So this is the gray curve, the continuous gray curve. So we can see that the trend of the curve is quite good compared with the same of the zone model, but the temperatures are higher than the temperature obtained with the zone model, and the fire duration is quite different because the fire is longer with FDS than for ozone. We also see a difference at the beginning of the simulation in terms of temperature, because with FDS we have higher temperatures around 200 degrees, whereas it's quite low with the zone model. We can explain with an assumption we made, because with the zone model we considered we have a spread of the fuel area, whereas in FDS we consider that all the fuel area burned from the beginning of the simulation. So we try to make a kind of interpolation of this curve in order to fit a little bit more with the zone model curve. So this is the gray discontinuous curve, but still we have higher temperatures and a longer fire scenario. So the conclusion is that we cannot validate the results obtained with ozone. That's the first point, because we have high temperatures and a longer fire duration. But at that step, we can ask the question if the compartment fire scenario is reliable or not for different points. The first one is the fuel, because we have several localized fire zones compared with a uniformly distributed fire load density. Okay, we have sprinkler installation with probably a good reliability, even if we cannot consider the sprinkler will activate at 100%. But the very important point is the last ones. We have large windows on facades, so very good ventilation conditions. So that's very important. And we ask the question, is the traveling fire scenario would not be more reliable than the compartment fire scenario. So we made some investigations with this scenario to replace with the compartment fire one. So the traveling fire, we can define it as a localized fire which is moving along the compartment. And we made some research on publications, because there were lots of research projects on this topic. And more particularly, Marion Charlier, who works on it, she made lots of experiments on this topic with different fire load density, different opening factor. So in this project, they highlighted a very important parameter for the traveling fire. So in the research, they highlighted a very main parameter, which is the opening factor, which is function of the windows area, on the walls area, and the height of the windows. So on the graph, we have some results for an office use. So we have fire load representative for an office, and with different opening factors. And we can see that with an opening factor more than 0.09, the traveling fire is very more reliable than the compartment fire scenario. So that's very interesting, because we could calculate the opening factor for our project, for our open space with the large windows on facades, and we get this opening factor 0.23. So we can say that the traveling fire scenario is more reliable than the compartment fire one. So we calibrated our traveling fire scenario model according to the publications, and also according to other studies. So we place our model with the compartment fire scenario. We replace the fuel into different combustible blocks located every 1 meter in the area, in order to increase the risk of spreading. We considered a
spreading conditions with the temperature. So we consider vents on each faces of the combustible block. The temperature reach the temperature of 250 degrees. The combustible block start to burn. And also a conservative assumption is that we consider the initial fire in the center part of the compartment in order to be far away from the windows. So here we can just compare the different fire parameters between the
Okay, so let's continue with the results. Here we will see a video of the simulations. So with the initial fire in the center part of the compartment, and then we will see the fire spreading. Okay. So at the first step, we keep all the windows, and yeah, at that moment we can observe the breakage windows and all the smoke disappears, and we have the front flame which is moving along the compartment. So this scenario is very representative of a compartment fire, of a traveling fire scenario. So it's the same up to the end of the simulation. So in order to get the results for our structural study, we located different poles into the compartment. So we located poles every 10 meters in the length of the compartment, and with temperature devices at different heights in the compartment. So here we have 3D view with the green devices, which are the poles. Here we have the results. So we have the gas temperature results of the first pole, so the pole which is the nearest from the initial fire. So we can see the temperature are quite moderate. And then we have the fire spread up to the next pole, so 10 meters away in each direction. So we keep the same thermal stresses around 450 degrees. And we have a short duration during the poles are exposed to the thermal stresses around 15-20 minutes. And that's the same for the other poles. We have the third one and the fourth one. So the next graph is very representative of the traveling fire. So we had all the results obtained with the poles. So we see that we have a traveling fire. So it's we have thermal stresses which are moving into the space. So the steel members will be exposed during a short time at different periods. So for the structural analysis, of course, we were interested in the adiabatic surface temperature, which are often used for thermal calculations and for structural study. So we allocated different AST device on the ceiling in order to catch the temperature. So it's interesting to see that we have moderate temperatures around 400 degrees, which is consistent with the temperature obtained for the localized fire scenario. So it's lower than the critical temperature for steel, which was around 550 degrees. So we can say that the R60 requirement is achieved for the steel members, or for the sailing beams, with this scenario of the traveling fire. So to conclude, we carried out the performance-based design approach in order to reduce the need of passive protection with several steps. First one, with a very simplified approach with zone models. We saw that we cannot really validate the results due to the limitation of this kind of models in terms of geometry shape and in terms of course, the surface. And we saw that we cannot really validate the result with the CFD model. And then we had the question if the compartment fire scenario was reliable or not. And finally, we kept the more reliable scenario, which was the traveling fire. And we could reduce the need of passive protection, so the client was happy with that. Okay, that's it. Thank you very much for your attention.
Yeah, thank you. One question regarding the structural analysis. So you deduced from the temperatures that were lower or maximum 400 degrees of Celsius that there is no need for a structural analysis because the strength of the steel is not lowered. But did you somehow make sure that there is no local failure like lateral torsional buckling for the ceiling beams, or did you test it somehow?
We could get deflections with this kind of temperature because, okay, the steel keep the same resistance as in ambient temperature because we are lower than 400 degrees, but we can have other consequences. So at that moment of the study, we just considered the thermal analysis to get some conclusions for the structures, but we didn't investigate with the structural behavior with such thermal exposure. No, we didn't investigate more.
Hi there. Yeah, really cool method. I was just wondering, your outputs seem to be all about the gas temperature. Have you considered the effect of sort of direct flame impingement or radiation from the flames on the, because obviously that would have a heating effect too.
Mm-hmm. With the simplified approach, we only consider the gas temperature. And then with the CFD approach, as we consider the adiabatic surface temperature, which is a quantity representative of a heat flux. So yeah, I think it's representative, but it's true that we could investigate a bit more for the localized fire scenario, maybe.
You simulated the failure of the glass windows,
yeah.
And this is, in my opinion, a crucial point. So at which point in time or at which temperature these glass windows will break, and this occurs very often in these simulations. There are different studies, so older ones where they say it needs a temperature difference within the window or within the glass of 300 Kelvin, and there are newer ones where this difference is a little bit lower. And I read also a study which is not public, but where they did a real test and found, okay, there are cracks at 300 Kelvin, but it breaks so that there's a hole only at 500 Kelvin. And so it's difficult to decide. What did you use as a criterion?
We used a document which is accepted by the Swiss authorities. So in function of the glazing, if it's a simple, double, or third one, we can consider these conditions. So it was our reference for this study.
Okay, well with that, thank you very much for your presentation.